So today we're going to talk about forces on an incline, and that changes the way that we look at our coordinate system just a little bit because we're looking at things on an incline, so things start to become tilted if we're looking at an incline. So before we look at inclines, we want to do a quick review on the forces that we've learned about so far. So let's start with the normal force. So far, we've only dealt with normal force acting straight up, right? If I have my free body diagram here and I've looked at my normal force, normally gravitational force goes down and the normal force goes straight up in the air, okay? So now that we're looking at an incline, we've got to shift our thinking just a little bit to review that the normal force means that it's the surface pushing up on the object. It does not necessarily mean that it's going straight up in the air. Okay, so the normal force does not necessarily mean it's going straight up in the air. It's going from the surface and it's going straight up from that surface. So if I were to draw my incline now at an angle and I look at my free body diagram, my normal force goes upward perpendicular from the surface. Okay, so this white line here would be my incline plane. My normal force here on my object goes straight up from that incline. It makes a right angle there. So the normal force now we have to think of as going perpendicular to our surface, not just straight up in the air. Okay, when we look at gravitational force, however, this does not change. The gravitational force of an object always goes straight down. Always, always, always goes straight down. It's not going perpendicular to that surface. The gravitational force always goes straight down toward the center of the earth. So here, if I draw my incline again, I've got my incline, I've got my object here. My normal force, like we said before, goes perpendicular to the surface, and my gravitational force goes straight down. Okay, so now these two forces are not directly offsetting each other. We've got this tilted inclined surface that's making it a little bit more difficult, and we're going to have to look at the components of one of these forces pretty soon. Okay, but now we realize that the normal force and the gravitational force do not directly offset each other on an inclined surface. So let's talk about what happens to these inclines. Okay, right here I've got my object drawn with our inclined surface. But when we work on an incline, we're going to rotate our axes. We're going to rotate our entire coordinate system so that we have the x-axis that goes along the incline. Okay, so now my axes run vertical axes here. My horizontal axis runs parallel or right with that incline. Okay, so this would be my y-axis. This would be my x-axis. Okay, everything shifts just a little bit kind of clockwise that we're looking here. So this is still the positive direction. This is still the positive x direction. This is the negative direction and the negative direction. Okay, so our coordinate system goes from directly north and south, east and west, to being shifted just a little bit so that it runs parallel to that incline. Our x-axis runs parallel to our incline. Okay, so what this does is that it takes away us having to work with components of a bunch of different forces. It allows us to work with fewer components, okay? So we rotate these axes so that we don't have to work with so many different components, okay? Because as I draw my forces here, force due to gravity goes straight down. The normal force goes straight into the air. If I had normal axes and I had a frictional force, let's say, if I had some applied force that was pushing it down, and I kept my normal axes like this, I would be dealing with components for 3 different forces, right? I would have a frictional force component, I would have a normal force component, and I would have an applied force component. And that's not what we want. We want to deal with as few as components as we can. So that's the whole purpose of us shifting those axes so that it runs along the incline. Okay, so now if you look at my forces again, my normal force would go straight up, directly up in the positive y direction. My frictional force might go in the negative x direction. My applied force here would go in the positive x direction. My gravitational force, however, has some components that we have to deal with. Okay, because now it's going at an angle, at some sort of an angle from the axes. So we've got a y component to our gravitational force and an x component to our gravitational force. And these both have specific names that we're going to cover here in just a second. All right, so I'm going to pull up this drawing that we just had here, and I want you to look at the fact that gravitational force has some components that we have to deal with, okay? Since the force due to gravity points straight down, we've got to work with these components of the force due to gravity. So here is our gravitational y component right here, and here is our gravitational x component, right? This goes parallel to that x-axis. It goes horizontal because we shifted our x-axis. And our vertical component of our gravitational force runs with the y-axis, okay? And the components of this gravitational force have a very specific name, okay? They each have a specific name. So the horizontal component of force due to gravity is something that we call force parallel, okay? And the reason that it's called force parallel, so the reason that the horizontal component is called force parallel, this is parallel, not an 11, that means parallel. The reason that it's called the force parallel is because it runs parallel to the x-axis. Here's our x-axis right here. This parallel force, the gravitational x component, runs parallel to the x-axis, so we call it force parallel. The vertical component of our gravitational force is called the normal force, okay, or sometimes it's called force perpendicular, okay, and the reason it's called that is because it is perpendicular to the surface. And just like the normal force, it's found perpendicular to the surface, so we can call it the normal force because these two forces, assuming there's no other vertical forces acting, would be equal to each other. Okay, assuming there's no other vertical forces acting, those two forces would be equal to each other. Okay, this vertical component of the gravitational force we can just call the normal force. Okay, your book might sometimes call it the perpendicular force because it runs perpendicular to the incline or to the x-axis. But we can call it the normal force because we know at normal conditions or under no other vertical forces applied that those two forces are going to be equal to each other. Okay, so let's go ahead and try some practice here. So if you need to pause the video to get it written down, you can. What's going to happen is I'm going to walk you through each step here that our problem takes because our overall goal is going to be to find the horizontal acceleration of this object. So that's going to be our overall goal, but I'm going to walk you through and the problem's going to walk you through every single step that it takes to get there. Okay, so like I said, our overall goal here is to be finding the acceleration of this box in the horizontal direction as it slides down the incline. So I'm going to go ahead and get my free body diagram drawn here. So here's my object. I've got a gravitational force. I've got a normal force. I don't have any applied force, nothing's pushing it down the incline, just going to have gravity be enough to do it here. We're not going to have any frictional force because it doesn't tell us anything about that. Make sure that we tilt our axes like it says here, and we're going to label the positive and the negative direction. So we always assume that toward the bottom of the incline is going to be the positive direction because that's the way that most objects are going to go. They're not going to spontaneously make their way up the incline. So that's going to be the positive direction. So these are the only two forces that we have acting here. And I'm going to go ahead and label those extra forces that we have. And when we draw the components of our gravitational force, it's really important that our component's right angle, the right angle of this triangle, is opposite of our gravitational force. Okay? Those two have to form a right angle. So the normal force and the parallel force have to form a right angle opposite of that gravitational force. Okay, so here's our complete free body diagram. So overall, with our goal in mind to find the horizontal acceleration of the box, we're going to walk through these steps that it takes for us to get there. Okay, first and foremost, we have to find F sub g, right, our force due to gravity. Force due to gravity is F sub g, and to find that, we always take mass times gravity. The mass was given to us at 10 kilograms times 9.8 is going to be 98 newtons. So what that tells us is that the hypotenuse of this gravitational little triangle right here, this little gravitational triangle that we make, the hypotenuse of that is equal to 98 newtons because that's our gravitational force, is equal to 98 newtons. Okay, so from there, we can start to find the normal force and the parallel force. Okay, and to do that, we're going to find the components of that triangle. Here is where our angle comes into play. It says that our incline makes an angle of 30 degrees with the horizontal. So what that means is that if we look at our incline, really 30 degrees goes right here at the bottom of our incline, and it also corresponds to the angle right inside our gravitational triangle, is also 30 degrees. Okay, that angle always matches our gravitational triangle. So we're going to take whatever angle they give us that our incline is at, and we're going to put it right in this little pocket right here of our gravitational triangle, so it's 30 degrees. Okay, so that's going to help us solve for our components. So if we want to find the normal force is adjacent to this 30-degree angle. It's adjacent, so we're going to take the hypotenuse, which is 98, times cosine of 30 degrees. Okay, and we're doing that because 98 is the hypotenuse, 30 degrees fits into this angle right here, and the normal force is adjacent to that, which means we really are using cosine. Okay, so what it would really look like this if you set it up, cosine 30 degrees equals the normal force, which is adjacent over the hypotenuse. So I took out one little step for when I multiply 98 across on both sides, and I shortened that into one step right up here. Alright, so if I do the math and I take 98 times cosine of 30 degrees, make sure that your calculator is in degrees and not radians. I'm going to take 98 times cosine of 30 degrees and I get 84.9 newtons. So solving now, taking our next step to solve for the parallel force, I'm going to use that same equation as I did up above, except I'll use sine instead of cosine. 98 is the hypotenuse. I'm going to use sine because my parallel force is opposite of that 30-degree angle. And for sine, I use opposite and hypotenuse. And that gives me a value of 49 newtons for my parallel force. All right, so now we've got our gravitational force. We've got both of the components of that gravitational force as well. Now we're going to start looking at the acceleration as it slides down the incline. So as it's moving down the incline, we know that it's not moving vertically at all. It's only sliding on the incline. It's not moving up and down off the incline at all. So we're only looking at horizontal forces. That means we need to find our net force in the horizontal direction. Okay, so we can put that X there to kind of keep us reminded that we're looking at the X direction. And the only forces that we have working in the X direction is our parallel force. Okay, and although it sits below the axis, it's still acting in the horizontal direction. Okay, it's a gravitational component that's acting in the horizontal direction. So that's our only horizontal force. And it happens to be in the rightward direction. So we're going to take F net in the X direction is equal to F parallel minus 0 because we have no leftward forces. So we can leave this minus 0 on. You can take it off, whatever you prefer. But we're going to solve for the acceleration in the horizontal direction. We know the mass, right? We can substitute ma equals force parallel. We happen to solve for force parallel, so we know that. We know the mass, so we can go ahead and substitute that in. I'm going to do that right over here. So I'm going to take 10 kilograms times A equals force parallel, which I solved to be equal to 49 newtons. And when I divide 49 by 10, That means I'm going to get my acceleration equal to 4.9 meters per second squared. So what this is telling us is that as this box is sliding down the incline, the gravitational force, or the force parallel, the horizontal component of that gravitational force, is enough to accelerate it at a rate of 4.9 meters per second squared down this incline. Okay, it's frictionless. We're not applying any force to push it down. This means we set an object on the incline and immediately it starts sliding, and it's picking up speed at a rate of 4.9 meters per second squared as it goes down the incline. Okay, so on to our next problem here. Go ahead and pause the video if you need to get this written down, but we're going to go ahead and start with drawing what's happening here, looking at what we're solving for. And again, I'm going to put up all the steps that it takes to get here, but I want you to follow along as we do the math that goes with it. Okay, so the first thing that we want to do is get our free body diagram drawn, and if you can do that by pausing the video first and then checking it, that would be a good idea probably. So here we've got a frictionless object, so we're not worried about friction. Our force due to gravity always goes straight down. Our normal force always goes perpendicular to the surface. That means that we're going to break down our gravitational force into its components, and we're going to label this side, the bottom side, the parallel force, the vertical side, the normal force. Okay, so here is our free body diagram, so we've got that done. We're going to find the parallel force. And this time, what does this 466 Newton object tell us? Okay, this 466 Newton object tells us that that's the force due to gravity already. That is its weight. Okay, since it's given to us in newtons, we know that it's a force. So we know that that is already equal to F sub g. So we don't have to go about solving for the force due to gravity because they did it for us. We do not take that 466 times 9.8. They already did it for us. So we're going to go ahead and solve for the parallel force. Parallel force is opposite or adjacent, and it is opposite of that angle. And we remember that the angle that they give us, this 33.3 degrees, fits right into this little pocket of our gravitational triangle here. So when we're solving for our parallel force, we're going to take our hypotenuse, which is 466, times sine of the angle that's been given to us. And I got a value of 255.84 newtons. Okay. Here, we don't have any reason to solve for the normal force because we're only looking at horizontal movement. We're not looking at vertical movement. You could solve for the normal force. It just so happens that in this problem, just like in the last problem we did, we don't really need it because we're not looking at vertical forces. We're only looking at horizontal forces. So we're going to go ahead and check parallel force off our list. We don't need the normal force. Like I said, you could solve for it. You don't need it in this case, so we're not going to go ahead and solve for it. Finding the horizontal acceleration means we're going to look at the net force equation in the x direction. And the only horizontal force that we have acting, same as last time, is our parallel force. Right? It's acting in the positive x direction. And there's no leftward forces here because it already told us it was frictionless. So that's going to be the only horizontal force that we have. And we're going to substitute mass times acceleration equals force parallel. And that's going to be the mass, which we have to find, right? We were given our F sub g, so we need to go ahead and find that mass, okay? And we find the mass using F sub g that's been given to us. So if we know that force due to gravity is equal to 466 newtons, we know that F sub g is equal to mass times 9.8 equals 466. So I'm going to take 466 divided by 9.8 to get the mass of this object in kilograms, 47.6 kilograms. And now I can use this mass right here in our net force equation. So I'll take 47.6 kilograms times A equals force parallel, which we solved to be 255.84. I'll divide that over. Divide the 255.84 divided by 47.6, and I'll get my acceleration equal to 5.38 meters per second squared. So now we've got our horizontal acceleration. However, that's not what our problem asked us for. It asked us to find how long will it take to get to the bottom. We're looking for a time here. Okay, so it gave us a distance that our object is going to travel. We now have our acceleration. So we're going to go ahead and I'm going to clear this off, and we're going to solve for the time now that it takes for us to get from this starting point that's 8.45 meters above the bottom of the incline down to the bottom of the incline. Okay, so we know that our acceleration is equal to 5.38 meters per second squared. We know that our distance final is equal to 8.45 meters. Because it tells us our incline is 8.45 meters long, which means that's how far the object is going to travel. We assume that it starts at the starting point at 0. Our initial velocity we assume is 0 because as soon as we set the object on the incline, it's going to start moving, but it's at rest for just a second. So we're going to go ahead and use our kinematics equation. See if you can press pause and figure out which kinematics equation that you can use. Go ahead and do that now. So we're going to use the kinematics equation that says dF equals di plus vit plus 1/2 at squared. Distance final is 8.45. Our distance initial is 0. Initial velocity is 0. And we're going to say 8.45 is equal to 2.69 times t squared. So we'll take 8.45 divided by 2.69. And then we take second square root of that answer. And that means t is equal to 1.77 seconds. Alright, so we're going to do one final type of incline problem here, and we're going to include friction, which we just learned about in the last class. And we're going to infuse that into our incline problems as dealing with friction as well. So now we're not looking at a frictionless incline. So go ahead and pause the video if you need to get this written down, and I'll go ahead and put the steps that we're going to follow up here to get this written down. But understand that our overall goal is to find the acceleration of the box as it slides down the incline, so we're going to find our horizontal acceleration. So I got rid of the steps so I had a little bit more room to write, and I'm going to go ahead and get my free body diagram here drawn so that you can see what we're working with here. We've got our force due to gravity. We've got a normal force. And we've got a frictional force, which opposes the motion, right? And the motion of this object is going to be sliding down the incline, so that means friction must be opposing that motion. We've also got to draw the components here of our gravitational force. This horizontal component being called force parallel, and the vertical component being called the normal force. Okay? So first thing that we need to do here is, since our mass is given to us in kilograms, right? We're given our mass, not our weight. We're going to find F sub g is equal to 20 kilograms times 9.8. And that gives us a value of 196 newtons. So that tells us the hypotenuse of that gravitational triangle. Okay, and we also, I forgot to include here, this 50-degree angle we know fits right in here. Okay. So we found our gravitational force. Now we're going to go about solving for the components of our gravitational force. We need both of the components this time because we've got a frictional force, and we know that to find the frictional force, we've got to have the coefficient of friction and we've got to have the normal force. So here we need both of these components. So let's go ahead and solve for the normal force first. The normal force is adjacent to the 50-degree angle, so we're going to take the hypotenuse times cosine because it is adjacent to 50 degrees. And we're going to take 196 times cosine of 50 and get a value of 126 newtons. We go about solving for the parallel force here. We're going to take the hypotenuse, which is 196, times sine of 50 degrees. And we're going to get 150.1 newtons. Next thing that we're going to go ahead and do is solve to find the frictional force, right? We've got our friction that we've got to take care of here. Our coefficient is 0.4, and we know our normal force. So just to review, the frictional force equation is coefficient times the normal force. So we know in this case our coefficient is 0.40, and we know that our normal force is 126 newtons because we just solved for it right up here. Okay, we solved for the normal force from that gravitational force. So that means 0.4 times 126 newtons gives us a frictional force equal to 50.4 newtons. Okay, so now as we begin to look at the horizontal acceleration, that means we need to set up our net force equation. So F net in the x direction, we're going to look at all of our rightward forces here. So our rightward forces will be force parallel because it's going down the incline in the positive direction, and our leftward forces is our frictional force. We've got two horizontal forces working this time, so we would take force parallel minus the frictional force. Because force parallel is going in the positive x direction on the incline, force of friction is going in the negative x direction on the incline. It's opposing that force. So we can start doing our substitutions here. If we take mass, which is 20 kilograms, times A, equals our parallel force, which we solved to be 150.1 newtons, minus our frictional force, which we solved to be 50.4 newtons, gives us 20 times A equals 99.7. And we will divide 99.7 by 20 and give us an acceleration of 4.98 or 5 meters per second squared, if you want to round that up. Okay, so that is it for inclines today. We will do some more review. Be sure that as you're working problems, if you aren't understanding or you're getting stuck, you go rewatch these problems again. See where we got these numbers from, see if you got stumped by drawing the free body diagram, all those kinds of things. Please just take advantage of that.